Hey everyone, and welcome to our lesson on data types. In this lesson, we're going to be talking a little bit more about the string data type. We're also going to learn about a few new data types such as lists, dictionaries, and tuples. And then we're going to wrap up talking about conversion, so converting between different data types, which we've already alluded to a good bit, as well as the math module. So let's go ahead and get started. We'll first start off taking a look at strings again. So strings can also be characterized as a sequence data type or a collection of objects ordered from left to right. So when we think about a string like Python down here, that is a string in itself, and it's made up of characters or single character strings that are one after the other. So Python. Well, there's a way that we can reference the individual characters in the string, and we call that an index. So, in computer science, it's sort of a running joke that computer scientists start counting at zero, and that's where indexes start at in Python. So, there are a couple programming languages that you'll find out there where the indexes start at one, but for the vast majority of them, indexes start at zero. So we can address these different characters based on their index position. So if I want to say talk just about the H here in Python, well that is the third character, the third index position. Technically it's the fourth character because it's off by one, being that we start at zero, right? So 1, 2, 3, 4, fourth character, third index position. Now we can access these characters out of a string if we want to get them just by using brackets, and we can also go negative if we want. So let's take a quick look at that in idle. So for this example, let's just work out of the interactive prompt, and let's create a string called myString and set it equal to Python like it is down here. So we had talked about if we wanted to pull the H out and just deal with it, that we could reference it by its index position 3. The way that we could do that is by using brackets. So let's try putting it in a print. So print myString, and then we can use these brackets to indicate the index position. So we would read this as print myString sub 3. And if we look at that, we see we get the H back. Now we could also assign this to another variable, such as, let's say, first char equals myString sub 0. So if I want to print out first char, we see that that's the capital P. And then I had also mentioned that we could work backwards if we wanted to. So Python's nice in that it gives us the ability to use negative index positions. And that's something that a lot of other programming languages don't give us. So the idea with that is, if we start here and we get an index position of -1, it's just going to wrap back around and go back 1. So we could do -2, and it's going to wrap back around and give us the O. -3 would give us the H, and so on. So let's test that out. We'll just do a print myString sub -1, and we see that we get the N. -2 gives us the O. Now, additionally, we may find it useful to find the length of a string at some point, or really of any sequence, and we'll see the usefulness of that later on as we look into some more of the sequence data types that are out there. But to find the length of a string, we can use the len function. So the len of myStr is 6. So notice the relationship between the length of a string and the maximum index position is off by 1. And again, that goes back to the fact that we start counting at 0. So we're going to be off by 1 when we take the length of something and look at the index position of that. So another way that we could get the last element is we could say, well, print myString, and then take the length of my string and subtract 1 from it. Right? Because that's going to give us 6, minus 1 will give us 5, and that's my last index position. Okay, so we still get the N there. Now, looking at this though, it's obviously a lot easier to take advantage of this syntax where we can just put in a -1 that Python provides us with. Okay. And we could also pull out the length and hold it into a variable somewhere if we wanted to. So if we wanted to say length of my str equals the length of my str, then we could use that later on and print that out if we wanted to. Okay, so just a couple more examples. This one's just of my string hello world and printing out the first character and the first character of the second word, world. So that would be in the 6th index position. And we can grab the size and print that out as well. So I encourage you to take this and just try to play along with that in idle, type it out, and just make sure you get the same results. Same thing here. This is just illustrating that we don't necessarily have to put a numeric literal inside these brackets, and I kind of alluded to that in this example where I had a function call in there, but here we're just using a variable like h index or w index, and it's perfectly fine to substitute those in as well. Okay, so a little bit more about strings. So strings are an immutable data type, and what immutable means is that it cannot be changed. So once a string has been created, it cannot be modified. And this is kind of a tricky notion to understand, but whenever we add something onto a string, what's really happening is we are going out and we're creating a new string from that. So let's take a look at an example of that. So what we have going on here is we have this myString variable equal to hello world, and in the 11th index position is this period. And let's say we want to modify that and make it an exclamation point instead. Well, unfortunately, we can't just simply say myString sub 11 equals this exclamation point because we get a type error, and the type error says that a string object does not support item assignment. So each one of these characters is looked at as an item, and it won't let us reassign what those are within the string. So if we want to tack an exclamation point on the end, there's many ways that we could do that, and in its most simplest form, we would just do a new assignment statement. So hello world exclamation point, and then we see that that's what's stored in my string. So to kind of make this a little bit more clear, let's look at this illustration. So we have this string s, and it equals ABCD. And then we go back and we say maybe that s equals s plus EF. So we're tacking on an EF onto the end of this string. Well, at that point, a new string is created in memory that has ABCDEF in it. And then s, instead of pointing to this string in memory, we lose that and we point s over here to this string. So effectively, this one is gone and it'll be deleted out of memory because it won't be used anymore. Okay, so that leads us into string concatenation, and we've been talking about string concatenation, and we've had to use it in order to solve some of the labs in the past. What we found is that string concatenation just adds characters to the end of an existing string. So it does create a new string. It is still immutable. Going back to this document real quick, you could think of this as s equals ABCD, and then s equals s plus EF. And if we print s, we see that it's pointing to this string over here, and that's the one that it prints out. But this one over here is gone. And I guess one other way we could look at that is we could say, all right, s equals ABCD, and let's look at the ID of s, because remember the ID is going to show us the memory location that s is stored in. So now if I say that s equals s plus EF, so tacking on 2 extra characters, if we look at the ID of S, we see that that is a different number, right? Totally different number because it's stored in a different position of memory. Okay, so string concatenation, really simple concept. We use the plus operator. The important thing to know, and I'm sure everyone's run into this a little bit, is that both operands must be strings. So what's on either side of that plus sign must be a string object. If it's not, we'll get I think it's a type conversion error possibly, or a type error, and it says that it can't convert a string or a whatever data type it is to a string implicitly. So we just have to do that explicitly. Alright, so looking at this example here, my string equals hello. We can create a new string by just tacking on, using that plus or the concatenation operator, an exclamation point, and then we can print that out. Now, over here is what I was referring to when I was talking about how both operands need to be a string data type. So looking at this example, we have a name. So remember, inputs always come in as strings. So this is going to be a string data type, Bob. And then we have an input for age. Excuse me. So we're bringing that age in. It comes in as a string, and we'll convert that to an integer and then store it in age, so 20. And if we try to build up a new string called output and say that name is blank years old, then we get this type error, can't convert int object to string implicitly. And the way that we get around this is we have to explicitly convert that object to a string. And the way that we explicitly do that is with the str function. So just very similar to the int function that we've been using, like up here to convert a string to an int, this will convert something else to a string, be it an int, a float, or whatever other type of data type it is. It's going to try its best to convert that to a string. Okay, so once we do that explicitly, everything's good, we don't get any errors, and we can print out the output and see that Bob is 20 years old. Alright, another thing that we can do with sequence data types is we can do slicing. And what we're going to look at here is string slicing. So I like this illustration of a pie because I think it shows well exactly what we're talking about here, in that when we do string slicing, we can grab a subset of the characters in a string. So we can grab a piece of the pie, so to speak. And the notation looks like this. So we have our identifier, or our variable name here, and then the brackets. And inside the brackets, instead of just putting an index position, we can put a starting position and then an ending position. And the thing to keep in mind is that we specify the start and the end, but the end is the index position that is up to but not including. Alright, so that's important to keep in mind. Optionally, we can specify something known as a stride, and a stride just determines how much to increment the index after reading each element. So if we want to skip every other character, we could have a stride of 2. By default, obviously the stride is 1, and we're just going to get every character then. So let's look at an illustration to try to hit this home a little bit. So we have this string here, Monty Python, and we can see the index positions up top, so 0, 1, 2, all the way up to 11. And conveniently, we also have the negative index positions down at the bottom. So remember, if we wrap around, we go back to -1, -2, and so on, all the way to -12. So if I just wanted to get Pyth, Pyth, out of this string, I could do a slice from 6 to 10. And if I just wanted to get Monty out of the string, well, there's a few ways I could do it. I could do a slice from 0 up to but not including 5, so that would get 0 through 4, the Monty string. Or I could go starting at -12 and ending up to but not including -7, right? So that would give me MONTY, -12 through -8 inclusive. So let's just see that in action real quick. We'll go back to our interactive prompt here. And okay, just get rid of some of that. Okay. All right, so let's say that my string is Monty Python. And let's just prove that this works first. So let's get Monty. So Monty equals my string sub 0 up to but not including the 5, right? Because that's after the one that we want to include. So put a 5 there, and I can print out Monty. And that's all that I got out of the string slice. Same thing here for Python, 6 through 10, or we could go and use these negative positions. So let's create one called pyth and set it equal to my string, and we want to start at, let's use the negative position. So let's start at -6, and then go up to but not including the -2. Okay, so if we print that out, let's make sure that it contains pyth, and it does. Awesome. All right, so something else I want to point out is that if we're starting at 0 or if we're going up to the end of a string, then we can actually just omit that part of the string slice. Let's go back into idle and take a look at this. So, for instance, we went from 0 to 5 to get Monty. Another thing I could have done is just went from my string, put a colon and a 5. So notice I omitted where the 0 was before. And if you omit it, it just assumes that you're starting at the beginning. Okay, so print Monty here, we'll still see Monty. Additionally, let's see, if I wanted to get the ON out of the end here, or the end here, I should say, let's just jump back real quick. That is at the 10th index position, the O, and the N is at the 11th. So I would have to put 12 in order to go up to but not including. But something else I could do is I could say ON equals my string from the, I already forgot, the 10th index position. And if we omit the end, it's just going to go to the end of the string. All right, so those two things can be very convenient so that we don't have to necessarily know what the ultimate index position is or find the length or anything like that. So let's just verify that that worked correctly, and it does. Now, looking at this example, we have a URL, facebook.com/index.php. A URL can be broken up into multiple parts. The first part of a URL is the protocol. And so this governs the rules of how we're going to communicate with that website. And in this case, it's HTTPS. And if we wanted to pull that out, we could use substrings to do it, or string slicing. So we can start at 0 at the beginning here and go up to but not including 5. So 0, 1, 2, 3, 4, 5. The colon is the 5. So we're going to get this HTTPS. And if we look forward a little bit, we'll see that when we print it out, that's what's stored there, HTTPS. The domain we could pull out from the 8th position up to but not including the 24th. And then the file that we're actually requesting from this URL, we could also get that, and instead of doing positive indexes, I just went backwards and counted backwards to -9 and went to the end of the string. So we can omit the end there, and we can see that when we print file, we get index.php, so the whole file name. Okay, so just illustrating the strides, I don't feel like we use strides as much as we do just regular string slicing, but I think it's still important to illustrate that so that you know how to do it if you come across a situation where you need to, or if you come across code that's using it, you understand what it's doing. So I've got a couple of strings here. Let's look at the first one is letters, and that's just A through Z, all lowercase. So if I want to look at every other letter, we can do this string slicing notation, right? And what's going on here is a few things. We're omitting the beginning index, so we're going to start at the beginning. We're omitting here in the middle the ending index, so we're just going to go to the end. And then we're specifying a stride of 2. So we're going to skip every other character. So in fact, I actually call this every other letter. And if we print that out, we see it starts at the A, skips the B, then we see C, E, G, I, all the way up to Y. And that's where we get that string from down here. It could also be useful to see odd numbers. So if I have all the single digit numbers 0 through 9 here, and we're looking at odd numbers, maybe I just want to look at the first one, so 1, up to but not including the fifth one, which would be 6. So 0, 1, 2, 3, 4, 5. It'd be 5 because we started at 0. Excuse me. So starting at 1, going up to 5, up to but not including. So we're only going to be looking at this 1, 2, and 3, and 4. But if we're skipping every other one, then we're getting the 1, we're skipping the 2, and we're getting the 3, we're skipping the 4, and then we're done. So printing that out, I just get 1 and 3, or what looks like 13 here. Alright, so moving into our next data type. This one is a container data type. It's also a sequence data type. So all of those things that we just learned about strings, where it deals with indexing and slicing, they apply to list as well. Now, the cool thing about listar is that we can put whatever we want inside them. I think this is a good illustration down here. When we create a list of something, we just sort of number them and we write out what it is. Well, in Python, to create a list, we give it a variable name. So you could call it my list, you could call it cars, or whatever you want, equals, and then in these brackets, we just specify the things that we want in the list. So these could be strings, they could be ints, they could be floats, or any other data type. And we just separate these things with commas. And something else to point out about listar, unlike strings, lists are mutable. So if I wanted to change later on what element 2 was, I could very easily just say, well, my list of 1 equals something else now, element 7. So let's look at a concrete example of how we do this in Python. So here's an example of a list of students. So this is a list that contains nothing but strings in this case. So we have Alice, Bob, and Charles, and the indexing works the same way that it worked with strings. So student sub 0, as you see here, is still going to be Alice. That's our 0th element. And we could work backwards, so student sub -1 is Charles. And we could also do a subset. So if I wanted to get from the first position up to but not including the third index position, which doesn't exist, so it's just going to get Bob and Charles, we can see that down here. So like I said, Lists are mutable, so if I wanted to change what was in Bob's position, the first index position, I could say student sub 1 now equals David. And if we print out students, we can see Bob is completely gone and has been replaced by David here. So lists have certain methods that we can use, and these methods just make it easy to add stuff to a list or remove things or to take the particular element off a list. So let's look at these individually. First we have the append method, and it takes a value or an element and it just adds it to the end of a list, particularly my list. So these methods work on the variable name. So if I have my list equals something up here and it's a list, then I can sort of access different functions that are available of that list that we call methods by using this dot operator. So my list dot append means append something to my list, and then in parentheses we just pass in what it is that we want to append. The mylist.pop, what it does is it removes an element at an index position from my list. So sort of looking back here, if I just wanted to get rid of Bob altogether and I didn't want to replace Bob with someone else, we could have done students.pop 1, because that would address the students list and it would tell it to remove what's at the first index position, Bob. So that would leave students with just Alice and Charles in the list. And then lastly, another way that we can remove an element is using the remove method. It differs from pop in a couple ways, but one of the ways is that we actually specify the value that we want to remove rather than the index position. So that would be the same as saying students.remove and then putting Bob in quotes in here. And this method would go and look in that list and remove the first occurrence of Bob that it found. So that's probably an important thing to mention there, is that when we're doing this remove, it's not going to remove all the Bobs if there's more than one Bob. It's just going to remove the first one that it comes across. Okay, so a couple of examples here of those methods being used. We can create an empty list. All right, those are just open close brackets. You could also use the list function. So something like students equals list. That also creates an empty list. Look at the type of students. We can see that that is a list data type. Lots of times though we just see this notation. It's just another way to write it. It's a little bit easier, I think. So if we print out students, we can see that it is an empty list. There's literally nothing in there. Now we can append some things to that, so let's put some things in our list. Students.append Bill and append Charlene. And if we print out students, we now see that it contains Bill and Charlene in that list. So this list students is keeping up with what we tell it to by appending. Now students.pop 0, that's going to remove the 0th element out of this list. It's also going to return it. So you can see that it prints out Bill down here. That's something that it does in the interactive prompt because we're seeing what this returns. But if we wanted to, we could actually capture that by using an assignment statement. So let me show you what I mean by that here. Let's get our own interactive interpreter going. And let's say that students equals Bill and Charlene. And let's say that student equals students.pop 0. So again, what it's going to do is it's going to remove this 0th element, but it's going to assign it to student. Okay, so now if we print out students, we see that only Charlene's in that list. And if I print student, I've got Bill. So I can use this later on. I can reference it if I need to, or if I didn't need it, it's perfectly fine to just say students.pop0 and not do an assignment. It really just depends on the use case of what we need in our program. Okay, and then what else can we do? There's that remove method. So students.remove Charlene. After we print students after that, we can see it's empty. And the only other thing I want to show you here is, let's do a students.append Charlene. And if we print students, we can see that it's got 2 Charlene's in it. So students.remove Charlene will actually only remove this first one. So we can see it still contains Charlene. So that's something you're going to want to keep in mind as you're using the remove methods, that it's just going to remove the first occurrence. Okay, so what are a couple of sequence type functions? So we've already seen len. Len will take the length of a list. So this Charlene, our students list, if I wanted to take the len of that, we can see that its length is 1. We can add lists together. So if I had other students equals, well, let's say Alice and David, then I could say maybe class roster equals students plus other students. So I'm adding this list that has Charlene in it with a list that has Alice and David in it. And if we print out class roster, we can see it contains Charlene, Alice, and David. So it actually retained the order too. Something else to notice is it substituted Charlene here, and then it tacked on Alice and David and just created one big list out of that. Now, if we have numeric data types, we can find the min, max, and sum. So I shouldn't just say numeric here, because even with something like the string data types, we can find the min here, and it's just going to find in the order that the characters go in, which one comes first. So let's see, what is the min of class roster? It should be Alice, right? And that's what we get. Alice comes before David, comes before Charlene. The opposite is true of Max. So Max is going to find David in this case, because that's the last element if we were to put this in ABC order. So class roster, and we see that that's David. This also works really good with numeric data types though. So let's take a look at an example of maybe my numbers. 1, 2, 3, 4, 5, 1,000, -1, and 3. If I take the min of my numbers, it's going to look at all of the numbers in this list and find the smallest one. Okay, so -1 gets returned. Same thing true if we look at the max, right? It's going to find the highest number in there, 1,000. Now, one really cool function is the ability to sum up all the elements in a list. So if we have a list like this, then we could just pass it to the sum function, and that'll tell us the summation of all of those numbers. So that can be really useful later on if we want to quickly find the average of a list of numbers, because what do you need to find the average of something? The average is going to be the total divided by the number of elements, right? So let's see here. So the average is going to equal the summation of my numbers. And do we have an easy way to find out the number of elements? We do. If we look in this list, there's the len function. So we could do the len of my numbers, And that's just a really easy way to find the average, right? Because we don't have to go through and tell it to add up this plus this plus this plus this. That's what the sum function does. If we print out average, we can see what the average of those numbers would be. And then there's ways that we can find the index of the first element in the list whose value matches a value. So let's see. What is the index position of 1000 in this my numbers list? Well, the syntax over here for the operation says that we specify the list itself dot index and then the value that we're looking for. So the list itself is called my numbers. I'm going to use that dot operator right here followed by index. And the IntelliSense here is showing us all of the different methods that we could call. So there are a few others that we're not talking about, but the most important ones are these append and remove and pop and index and count that we're covering here. So what is the index of this value? 1000? 5. I could verify that. 0, 1, 2, 3, 4, and at the 5th position is 1000. We could also try to find the number of occurrences of a value in a list. So looking up here, most things are written only once except for the 3. So let's see if we could count that and get a 2 back. So my numbers dot count the number of 3's. And we can see that that happens twice. Okay, so just another example there of doing some averaging using the index function and so on. Basically what we just did. The next data type I want to cover is very similar to a list, except for this one is immutable, meaning that once we've created this thing called a tuple, we can't change it. So tuples are really useful when we're dealing with data types that we're not going to change, such as, let's say, the coordinates to something. That's not going to change, so there's no reason to put it in a list. Instead, we can make it into a tuple. So White House coordinates equals this. And we can still reference the things in here. So, for instance, to print out the latitude, we could say White House coordinates sub 0 will give me that 0th element. White House coordinates sub 1 will give me that first index position here. We can see the printout over here. But if I were to try to change one of those coordinates, I'd get an error saying that the tuple does not support item assignment or something along those lines. And that's because it's immutable, just like the string data type. So moving on to dictionaries. Dictionary is referred to as a dict in Python, and it maps unique keys to values. So we've been indexing with numbers and talking about index positions. Well, there's another way that we could sort of index into a data type by using something other than numbers, like perhaps a string or a different immutable data type. So let's talk a little bit about the formalities of it, and then we'll look at an example. So a dictionary maps a key to a value. Alright, just like a dictionary, when we look up a word, it maps a word to its definition. A key can be any immutable data type. So a key could be a tuple, a key could be an integer, a float, a key could be a string, but a key could not be a list, right? Because lists are mutable. The value itself, though, can be any data type. So the value could be anything you want it to be. And the way that we access values is based on their key. So we use this in place of lists when there's an associative relationship. For instance, let's say that we're creating a dictionary for a person. We might have a key for name that has a value Bob and a key for age that has a value 20. So let's look at an example of that. So here's a dictionary called class averages. and a class average is just going to be a mapping of the student's name to their actual average in the class. So it looks like Alice has a 94, Bob has an 85, Charles has a 78, and so on. And just to talk a little bit about the syntax here, so to define a dictionary, we need to put them in curly braces. So a curly brace, an open curly brace starts the dictionary, a closing curly brace ends it, and then we separate our key values with commas, right? So we can see these commas in here, and in between each comma is a key, and then a colon followed by its value. So key value, comma, key value, comma, and so on. Now, if I want to print out Alice's average, there's going to be a few things going on, and this is why it's very important to keep all of these rules in your head about, data types and concatenation and pulling things out of dictionaries. So if we want to get Alice's average, we can get that out here. We can see that it's 94. So class averages, we specify the key here. So Alice is going to grab the value associated with that key. So it's kind of like indexing, but we're indexing by strings in this case. So the Alice index, not necessarily an index, it's the Alice key, returns 94. 94 is what data type? It's not in quotes, so it's not a string. Instead, it's an integer, it's a whole number. So we need to convert that to a string before we can concatenate it onto this Alice's average was string. So when we print that out, we can see that Alice's average was 94. And another way to look at this would be to sort of pull things out separately. So let's say we want to look at Bob. So our key is Bob. The average is going to be class averages sub key. So it's going to look in here for Bob, find the 85, and return that and store it into average. And again, before we do any concatenation, we need to convert that to a string. Now, if we try to reference a key that does not exist, we're going to get something known as a key error. Okay, so anytime you get a key error, it's going to show you the key that you were trying to get, and just realize that that means that it doesn't exist in the dictionary, right? Okay, a few more uses of dictionary here. We can create an empty dictionary. Just like how we created an empty list, we're just going to use that syntax that we use to declare a dictionary and just not put anything in it. So open curly brace, close curly brace, and if we print that out, we can see it's an empty dictionary. When we want to add things to a dictionary, we don't need to bother with append methods or anything like that. We can just reference the key for the first time. So even though Alice isn't in here, we can say that class averages sub Alice equals 100. And if we print out the dictionary then, we can see it now contains that key and that value. We can update things by simply just doing an assignment statement. So class averages sub Alice equals 95. So that's going to get rid of the 100 and now make it be 95. And if we ever want to remove something from a dictionary, we just use the del keyword. So del, obviously short for delete here. Class averages sub Alice. So we're telling it to delete something out of this dictionary, specifically this key here, Alice. And since that was the only thing in our dictionary, when we print it out again, we can see that it's empty. Alright, so at this point, this should be a recap. What are our common data types? We have ints, so those are whole numbers. We have floats, those are also numeric types, but they have a fractional component, so something after the decimal place. We have strings. These are sequence data types. They're used for text. We have lists. They're also sequence types, but they can hold any element that we want to put in there. And also they're mutable, meaning we can change the elements that are in there. A tuple, also a sequence data type, is basically identical to a list except for it's immutable. And then we have that dict or the dictionary data type, which is a mapping type and is just a container of key values. So these last three are different ways that we can order multiple objects or elements together. And when we use them, it's just going to be based on our use case, which one makes the most sense, right? Additionally, we need to perform type conversion sometimes. You'll also hear this referred to as type casting, just depending on the language. So we've learned about three different types of functions that will allow us to convert from one data type to another. So I won't hammer on about this too hard because I think we've already covered these pretty well. The int function takes one parameter. We can put it in there and it will try to convert something to an integer. So it can convert ints, floats, and strings with integers only. If we try to do a string that has, a character in it, we're going to get an error saying that it couldn't convert to the integer. The float data type, it works the same way. It converts ints, floats, and strings with integers or fractions to a floating point data type that we can then use to do mathematical operations with. And then lastly, we have the string data type that's going to basically take anything and try its best to turn it into a string. And that can be useful when we're doing string concatenation. Okay, so the classic example here is from an input, everything comes in as a string. So if we look at the type of height here, we can see it's a string. I can convert that to a float if I would like to. Okay, we can print that out and it's still 36.4. And I could also try to convert that to an integer. Notice what happens when we try to convert a float to an integer. It just loses the fractional component. That part doesn't fit into an integer, so it just drops it off or truncates it pretty much. So if we do height equals int height, that's going to convert this float to an integer and then reassign it to height. And if we look at the type, we can see it's now an int. And if we print that out, we can see that it's 36. Okay, so string formatting. We've learned about many different ways that we can build up strings. Particularly when it comes to printing out a string, we've seen how we can separate our variables and our literals with commas, or we could do string concatenation. Well, I'm going to show you one more way that we can build up strings, and this way is, I think it's the easiest way. It takes a little bit to get used to, but once you get used to it, it's a lot easier than doing concatenation or separating things with commas because we just don't have to do that. So let me show you what I'm talking about here. I think it'll make more sense. String formatting allows programmers to specify placeholders in a string, and those placeholders will be replaced with a certain variable. So placeholders, also known as conversion specifiers. More specifically, they're conversion specifiers. And they start with a percent sign followed by a conversion specifier type. So, what types have we learned about so far? We've learned about integers, floats, and strings. Well, %d is to replace an integer with. So the way that I remember this is I think D is for decimal, and when I think decimal, I don't think decimal point, but I think base 10 whole number. So I don't know if that'll work for you. It works for me. That's how I keep it up in my head. Because naturally you would probably think that should be %I, but it's not. It's %D. So we need a way to remember that. %f is for a float. So everywhere in a string that contains %f, we'll be able to sub in a floating point data type. And then if we want to sub in a string, we just use %s. So let's look at an example here. Let's look at the syntax and see how string formatting works. So we have three variables. We have a string, Bob. We have an integer, hourly rate. And we have a float, hours worked. Now, in its most simple case, if we are just substituting in one variable, we can do our syntax this way, where we have our string. So, hi, my name is, okay, %s period. This %s is just a placeholder. That's where we want to put Bob. After we close our string, the very next thing is a %sign. So far we know this %sign is the modulo operator. If the operand on the left-hand side of the modulo operator is a string, then it's going to do a string conversion rather than the modulo operation. Okay, so that's how it knows what to do here. It's aware of its operands. And then we put the variable that we want to sub back in on the right-hand side. So string, %sign, and then variable that we want to sub back in. So what this is going to do is, it's %s, so this variable right here is a string. It's going to sub right back in here, and we can see the printout contains Bob. So the nice thing about this is we didn't have to close our string and then do a concatenation and then write name. We were just able to write out the string one time the way we wanted it to look. And I think that we really start to see the benefit when we start doing it with more variables than just one, right? So last week I worked for %f hours, so that's a float, for %d dollars an hour. Okay, so same thing here. We have our string literal. It has our format specifiers in it. We have our format specifier operator, the %sign. And then what follows that, if it's more than one variable, so more than one thing that we're going to be subbing into this string, we have to put it in a tuple. So quick recap, what is a tuple? Well, it's like a list, but it's immutable. We can't change it. And the way that we define a tuple is with parentheses instead of brackets. So in these parentheses, we put our elements separated by the comma. And these need to be in the correct order. So as we're going through this string from left to right, the first conversion specifier we come across is going to get replaced by the first element in this list. And then it's just going to go to the next one, so %d would be replaced by the second element in the list. Now the data types have to be right though, because if we were trying to sub in like name here, it wouldn't be able to sub in a name for a floating point type. Okay, so that's why we have to keep up with our data types and know what we're dealing with. We can see that when it prints this out, it says last week I worked for 15.2000000 hours for $10 an hour. All right, we can take that a step further. And one really good reason to take this a step further is we don't need all these zeros here, right? We need a way to be a little bit more powerful and say, you know what, I only need this much precision, or only need to show one digit after the decimal point, or I want for you to take up this many character positions and that's it. Okay, so we can build on what we just learned about these conversion specifiers, and we can do things like specify a field width. So %5s, well, that's going to take up 5 character positions with that string. We can also specify alignment. So by default, we're going to right justify everything. But if we wanted to, we could left justify. So let's say we're taking up 5 character positions, and maybe we've only got 3 characters. then we sort of have a small box to work in, but we're going to have two spaces in the front at first because it's right justified. If we put this negative sign in there, then it's going to be left justified, and we'll have our three characters followed by two spaces. That way it still takes up 5 in total. And then lastly, what I was just showing you or talking about here in this last slide, where we don't really need all of these zeros, we can specify precision, and this really only applies with floating point data types. So what we do is we use a decimal point, so percent point something f, and that something is the number of digits we want to show after the decimal point. So if we had said 0.2f here instead of just f, then it would just say 15.20, and we wouldn't have all these extra zeros on there. Okay, so looking at an example here, we have Bob, and let's say we want for Bob to take up 3 character positions. Well, that's kind of trivial because Bob's going to take up 3 anyways, so that's really no different than just using %s. But look at this one right here where we say hello %10s. Well, this is going to take up 10 character positions with Bob. So I shouldn't have this period highlighted because that's actually outside of this, but starting here from the B and working backwards, all of this highlighted stuff up to the lowercase b is 10 characters. So we got 3 taken up with what we have, and then we have 7 characters of spaces because we said that we wanted this to have a field width of 10. So remember what I was talking about when I said that things are right justified by default. That's why this is hugging onto the right side over here. If we had %-10s, then Bob would be way over here and we would have all of these spaces and then the period. And I guess it's important to point out that if our string is going to take up more than the character width that we specified, well, it's just going to overflow it. So it's still going to say Bob down here. Okay, cool. So here's our good example of that %10s Bob. We can see that we have 3 characters here and then there's 7 spaces. Okay, sort of fitting in the same boxes below that's highlighted. And if I do a -10s, then it's left justified and we have 7 spaces here followed by a period. And then here is our floating point string specifier. So 0.2f shows pi, which I have it to not sure how far out precision wise, but a good number of decimal points. If we do 0.2, it's only going to go to the second digit, so 3.14. And if we wanted to, we could combine this with the field width as well, right? Like what we were doing here with the whole number 10 and -10. We can still do that. So we can say 10, so that's going to be a character width of 10 positions. 0.2 is going to be a precision of 2 decimal points, and it's going to be a float. So looking at sort of this box right here, we have 4 characters for 3.14, and we have 6 characters of spaces so that it takes up 10 altogether. And of course we could combine that with what we've learned about left justify and make that -10.2f. So whole thing's really not all that bad. It's just a matter of remembering these letters for the data types, remembering the point something to specify precision with floats, remembering that a whole number in front of one of these characters specifies field width, and that the negative will left justify it for us. Alright, so sort of wrapping up our video here, let's talk for a quick second about modules and then look at the math module. So modules are Python code that's located in a different file. And we just need to import a module and then we can start using parts of that file. So, for instance, there's this module called math, and it contains a bunch of functions that we would use to do math, like cosine, tangent, absolute value, things like that. And if we import that into our script, we can just automatically use that, and we don't need to write any of that code ourselves. So modules are like little chunks that we can use and plug into our program to build something bigger. Okay, we have been talking about functions for a while, sort of informally. Let me just formally introduce functions here. A function is a list of statements that can be executed. You could almost think of it as a subprogram, just something really small. Um, and the way that we execute it is by referring to the function's name followed by parentheses. So those parentheses is where we pass in things called arguments or parameters to that function so that it can work with it. We've been using functions pretty much since day one in here. We're pretty familiar with the print function now, the input function. Uh, Print takes an argument of a string and writes it out to the console. Um, this diagram does a good job of showing a function, I think. It takes some inputs, right? It does something, probably something with those inputs, and then it outputs. So it gives us something back. So like the print function, for instance, takes that string, it does something with that string, and it writes it out to the console, and that's sort of the output there. So a function call is when we put those parentheses on it. When we do that, we say that we're calling the function, we specify any arguments that need to go in there, and then control of the program jumps to that function, it executes, and then comes back to our program. Okay, so math module. Math can be hard, right? There's all sorts of functions out there or formulas that we need to keep up with. And fortunately for us, the Python language comes with a built-in math module that does a lot of this for us. So it performs many advanced math operations, provides some useful functions and constants such as pi and e. And the way that we use it is we just import math and then we use the math namespace. So you can always jump to documentation. If we look at the documentation for the math module, and just a heads up here, docs.python.org/3 is where you'll find the documentation for Python 3. If you are looking at python.org and their documentation, try to make sure that you are looking at the one for Python 3 and not the one for Python 2. Okay, so as we look through here, we can see many hopefully familiar functions like fabs returns the absolute value of x. We have ceiling for the ceiling function and floor for the floor function. Greatest common divisor. Oh, what else? So we could raise something to a power, raise e to a power, um, raise a number to a power, so x to a certain power. So find the square root of something. We have trigonometric functions, angular conversions, so degrees to radians or the other way, hyperbolic functions, special functions, and then we have some constants down here. And then the biggest ones that we'll probably use are math.e, so that's the constant 2.718281, and then math.pi. We can use that when we're doing formulas that require pi. So keep in mind that you can come and look at this documentation. Documentation is fairly easy to read through. So if we wanted to find the, I guess the arc sign here of x, then we would just say math.asine and then in parentheses the x, and that would return to us a number in radians. Or I'm sorry, it wouldn't return to us a number in radians. It would return to us the arc sign of that. It's expecting an x to be in radians. Okay, so the book sort of characterizes these as well in a nice little table, just to show you Most of these, not all of them are listed as we saw in the documentation there. But let's look at an example real quick of how we could use the math function. So before we can do anything with what's located inside the math function, we need to import it. So at the top of our file is where we normally put these imports. So before we start writing any other code, we can say import math. So that's going to import our math module, and it's going to bring in something called a namespace. And a namespace is just an area that variables or identifiers exist in. So the namespace that it's bringing in is math. So that in our program, we can reference that namespace. We can say math dot pi, and that's how we access things within the namespace. That's how we get pi out of the math module. So I can print that out. Notice that I'm using conversion specifiers, and you'll probably notice that the rest of my examples this semester are going to primarily use conversion specifiers. I highly recommend that you become comfortable with those. So we can print out pi, we can print out e, and we can use some of those functions that we saw in the documentation just by calling them, just by saying math.ceil of 10.4. You can see that that's 11. It's going to go up. The square root, math.square root of 144 is 12. Alright, so that wraps up the video for this week. Hope you guys are enjoying things. As always, if you have any questions, please feel free to reach out to me. If not, I'll see you guys in the next video. Thank you.